Good evening, and thanks for the invite to come down today. Yes, today's topic that I'm presenting to you is quite a current trend in London. It's regarding blind spots with large goods vehicles, as well as buses, and the vulnerable road user, i.e. pedestrians and cyclists. I'm sure you're all familiar with those types of collisions and the difficulties that we have with identifying what can a driver see, what can't they see, and hence the title. They're there to be seen, or are they? And hopefully this will give us some clues. But just some brief statistics. So in 2016, there were that number of fatals and that number of serious injuries, which is an awful lot of people. And going on from that, you would break it down, you're looking at 273 fatals involved in goods vehicles, 55 with pedestrians, and 16 of those were cyclists. And staggeringly, each fatal collision, in real terms, costs £3.5 million thereabouts. And then you probably can't put a figure on the civil side of things and the costs that are generated there. So the difficulty with large vehicles is where do you place the driver, and it creates a problem in that where the driver is sat, which is normally that sort of height, about 2.5 metres above the ground and potentially a metre or so back from the windscreen, straight away you've got a problem with direct vision, what you can actually see from that driver's position. Can you see the road surface, and how far in front of the vehicle can you see? And then the same applies to the side windows. By design, I mean, this is just the way trucks have been designed over the years. So the first case study I'm going to talk about is a typical UK town scenario, pedestrianised, mainly pedestrianised. This is pedestrianised at certain parts of the day, and other times of the day vehicles are allowed to come through. And this particular collision involved an elderly lady who happened to walk around from that junction on the left, where you can see the policeman stood just behind him. There's a side road. She's walked down. Now, the truck itself was stationary at the time as she came round the corner. But then he started to move. But she was walking along his offside. And then she did actually walk in front of him. So obviously before he'd started moving. So her movement is along the side and into the front. I'll just point out to you on the vehicle, you will all be aware that they've got lots of mirrors on them. So, just to point out, you've got the Class 2 and Class 4 regulations state that they must be fitted. The Class 2, the big one at the top, gives you the long view along the back and down the side of the vehicle. The one below it is a proximity, a wide-angle mirror, which spreads the view out along the side of the vehicle. Above the near side door, just there, is the Class 5 mirror. That looks down, directly down the side of the vehicle, looking at the road surface, a certain area. And in front there, looking down around this sort of area, is the Class 6 mirror. So they're regulated. They have to have those. Now, we've at TRL have put together this method of identifying the fields of view, the zones of visibility for both direct and indirect vision. I'll explain what those are in a minute. So we've got this device that we use. Ideally, if we've got the driver, the actual driver of the vehicle, we'll ask him to come along and we'll sit him in the seat, get the engine running. The seats are normally air suspended, so he needs to sit in it with the engine running, and it will put it up to the right height for him, for his weight. And we then measure the bridge of his nose. Where is that in relation to certain parts of the vehicle, so that we can fit the Heath Robinson device here to the steering wheel, and it's got a gimbal on top which pivots at the back here to replicate the neck where you would naturally pivot your head, and then it's got the eyeball. It's got the gimbal on there with a laser pen that sits. It's one of those, about £13, and it. In fact, that's a better pointer, isn't it? So that sits in there, and you're able to then use that to identify around the periphery of the windows. So if we start with the windows, front windscreen, this particular scenario, we're going to be concentrating on the door windows. And so from there, you try and squeeze in, and then you angle this pen around the periphery so that where it hits the ground, so it literally just touches the edge of the windscreen, the bottom of the windscreen, the dash, and then it continues down to the ground. And you can see that's just to give you an idea. So where it hits the ground, we will place a marker, a reflective marker, and we'll do that for along the front of the windscreen and a little way up, because you don't really need to know the top of the windscreen because that goes to infinity. So we are going to concentrate on this sort of bottom half, and you'll find that things like sat-navs on the windscreen, mobile phones, the steering wheel, the windscreen wiper blades, create a profile on the ground. We then laser scan. Once we've got all our markers down and we've got all our lines, so we know exactly, we've photographed it, we know exactly what relates to what, we are then able to laser scan the vehicle using a 3D laser scanner. So we scan around it, and that allows us to create a 3D model of the vehicle. So the 3D model of the vehicle is combined very often with a 3D model of the scene. So we'll laser scan the scene, or the police may have already laser scanned it for us, and we'll ask for that data. Once you've created your 3D model, you can then, using that visibility study where you've laser scanned and you've used your laser pen, so these would be where you'd have the markers on the ground. So from the driver's eye point down across the top of the windscreen, dashboard, down to the ground, and you create this coloured zone. So anything above that green zone is within the driver's direct vision. He can see from his position anything above that green area, and the same on the offside here with his windows. So anything below that orange zone, he would not directly be able to see. And importantly, it identifies these gaps, which I'll discuss in a minute. And that's just to show you the view from above, overhead view, to show the sort of spread that you can get through the windscreen. And then this is just a slightly different angle. So this is showing indirect vision. So direct vision is where you're using your eyes to look at an object through the windscreen. But indirect vision is where you're going to then use a mirror or a camera or a screen to actually see an object. So indirect vision is via the mirrors. And this shows you the Class 6, Class 2, Class 4 mirrors, which I've explained. The Class 6 mirror at the front. So anything within that cone, so it's slightly different with this, anything within it is visible, anything above it is not visible. So it's complete opposite with direct vision. But this one on the side here, this is showing the limit of view to the front. So anything rearwards of this would be in view in the mirror. And the same with this one. That's the wide angle mirror. So sorry, that's the Class 2. This is the Class 4, the wide angle. That's the normal sort of angle mirror. So anything down here would be visible, and anything down here would be visible. See, there is a bit of a cross match, so you can sometimes see in both mirrors the same object. And that's just an overhead view to show those zones as well. So again, here, anything within that coloured zone is visible back, and anything rearwards is visible there, and anything within that is visible in the mirror. the method we use for when you've got a pedestrian or a cyclist. So in this case, we've got a pedestrian. So we want a model to show within the 3D model, the overall 3D model, we create this cylinder at the right size and everything to match the pedestrian. And then it's placed within the model. And so what that's showing you, direct vision, so windscreen and side windows. And it's showing you that they're not visible. Those cylinders are only just touching the bottom of the zone, so they're not actually, the person is not directly visible. But it also this is the important point, the blind spot. So it nicely shows in 3D, because the work in 2D is fine, but you really want it in 3D because you want to know what part of a person can you see. You know, in 2D, if you were looking down on this, like we are here, you stand somebody there, you'd say they're in view. Of course, they might not be, because how tall are they? Are they kneeling down? That sort of thing. Whereas at least with this, you can identify what part of a person is visible. And so a slightly different angle. So the tops of the two cylinders that you see here and here, they are visible. These three cylinders are all visible in the mirrors. So that's the class 2, the class 4. So it shows that part of the pedestrian would not be visible in those two, but all of the pedestrian visible in the mirrors is available to be seen, assuming the driver is looking at that mirror at the relevant time. So and of course this case hangs on, is the pedestrian visible as she walks down the side and out into the front of the vehicle. So this shows you that on the class 6 mirror, all of those cylinders there, if that's the person, they are visible in that mirror. If you look in the mirror at that point, you would see them. Here, only the bottom sections are within view of the mirror. And it is quite a difficult mirror to use as a driver, because it almost turns everything back to front. So that's one particular study, and what happened on this case, this is a criminal case this was, within 25 minutes the jury, having seen all of that, again, well, you know, due to this study, clearly shows and assists, and it all hung on the fact that she was actually in the blind spot. When he decided to set off, at that moment, you know, you combine your investigation with all the evidence you've got, all your witness evidence, any CCTV, you can time it, you can position where she would be, what sort of speed is she moving at. And they actually found that she was actually in the blind spot, those two small areas, when he set off. You know, he's got the task of looking in the 2 mirrors on the right, 2 mirrors on the left, the class 5, the class 6 before he sets off. And he's going to be moving his head around. If he's not looking in the right place at the right time, he won't pick up necessarily the pedestrian. And in this case, he didn't. But the jury would have to say, well, she's in the blind spot. He had no chance of seeing her. And actually acquitted. He was acquitted. So that's the end of my presentation. Thank you.